All right, thanks. So for this lecture, if you want to follow along, you should check out the in pCoffee, the day 2 solution branch in somewhere. That's for a bit later. You don't need it immediately. You can have some time. And also, if you want to follow along, I'm also going to do some demos outside of that, a bit like what Max did the other day. So you also need the latest version of the lectures repo, which is what S3 something lectures. So just update that. I even updated them last night. So if you haven't pulled in a while, pull that one to the latest version, and you'll have the. And that's just if you want to follow along. You don't need to right now. So what I'm going to talk about today is profiling and optimization of code in Python. And I struggled a little bit with this because it's such a diverse group of people working on very different projects. So some of this is very applicable to everybody, but then it's very hard to come up with ways to optimize code without knowing what kind of code you're actually optimizing. So that is where that came from. But we'll see as we step through. I'll give some examples, and hopefully it'll be interesting and useful for everybody. Okay, so where are we now? So after the last week, last Friday, you basically have some code that's developed that kind of does something that you like. It makes a plot, et cetera. And you've verified that it works, meaning that there's tests that you've implemented and there's good test coverage. If you didn't get through all of that, of course, you just pull the day 2 solution. You can do pixie run PyTest, and you should get a bunch of tests that Vincent wrote. But you basically have code that you know works. And that's always the good starting point for this sort of lecture. But the problem is, imagine you want to run this code a lot, or on very large data sets, or using much more complex algorithms. And at some point, you find that speed or the use of memory on your machine is becoming a problem. So either it's taking, you want to run it multiple times and it takes 20 minutes to run, or maybe 2 days to run, because at least in my field, we often have people doing simulations or other things that take a very long time. At that point, it's really annoying and difficult to work with your code. So you want to figure out what ways can you make things go faster. Now, I give a caveat here that the code that we're working with, this pCoffee code, is already super fast, and there's absolutely no need to optimize it. So that's why I tried to come up with some artificial other things we can play with. But usually this is the thing that only is an issue if, when you start to deal with larger data and start to deal with more complex things. So what you'll learn in this lecture are, first of all, what causes performance to be poor and why. In particular, I'm going to talk about Python because that's sort of the subject here. It's a little bit different depending on the language you're using, but we'll explain that. And then the main thing really is how to identify slow parts of your code and maybe speed them up. And then how to identify maybe poor memory usage parts of your code and how to maybe fix those. Originally, this was going to be 2 lectures, but I realized that these things are so interleaved, and I actually ended up last night kind of rewriting it and putting it all into one sequential lecture. So what I'm going to do is just keep talking until and making some demos until the coffee break, and then we'll just continue with whatever's afterwards, after the break. So if someone, maybe tomorrow, someone could give me a 10-minute warning before the coffee break, I can try to make sure we're at a stopping point at that point, but otherwise, I think it should be fine. And obviously, feel free to ask questions at any point during this lecture. So the first topic is, why is your code slow? And like I said, I think it's sort of a bad example. The pCoffee example is not a good one for this because actually it's not slow, but it runs in a fraction of a second. But often when you're writing Python code, you end up with code that takes longer than you would like. So I forgot to delete a few of these things that appeared here. But anyway, there's a difference between what we call interpreted code and compiled code. And so this is something important to understand before you understand why Python code can be slow. So when you talk about compiled code, what usually that means is you have some sort of code written down. You run a program called a compiler, which also, by the way, has something inside called an optimizer, which takes the code and figures out the best way to turn it into machine code, and usually makes an executable. And at this point, you can throw away the code and everything that happened before, and you just get a binary here. And that's what most of the stuff on your computer is. When you get in Windows, you have an exe file, or on a Mac OS, you have a binary package. In Linux, it's usually things in / user bin. These are just binaries that have that have been precompiled. They run very fast, but if you look inside them, they're pure, just binary machine code. You couldn't read them anymore. So the code is gone. And these things typically run about as fast as you can on the computer. The other kind of code that happens in a lot of environments is what's called interpreted code. There you start the same thing. You start with some text as code. There's an interpreter that generally goes through each statement. It's not quite true, I'll show you in a moment, but and turns those into some sort of machine code instruction, which how this happens can be a bit different depending on the language. But this means that at the end, you don't come up with an executable. You actually are basically stepping through the lines of code in the text. There might be some translation to instructions first, but then there's a runtime environment that executes those and turns them as they're executing into machine code. So you always are kind of doing a translation step at the end into machine code. You never actually store the machine code on the disk. So Python is actually in the second class of interpreted languages, and what it actually does is it does. So it's not quite right to say it doesn't compile. People look at it, and especially when the first time you run Python on a script, you might notice there's a PYC file that appears somewhere in the directory. That's actually the compiled output of your program. So your Python actually does compile your code, but it compiles it to something called Python bytecode, which is basically an intermediate representation of your, so it doesn't look exactly like the code, but it's some easier to process intermediate representation. But it's not actually machine code. But the bytecode is sort of easy to translate into machine code afterwards, and it's basically machine independent. And that's sort of nice that you can run Python code, even the compiled Python code I think will run on any machine that you give it to, even if you have the PYC file with maybe some slight variations. And then later on, each instruction of this bytecode gets executed by the Python interpreter and turned into machine code and executed. So it looks more like this. It's like code, compiler, bytecode. Then the interpreter takes that information that's already been, once it's been compiled, and then goes line by line or instruction by instruction, turns it into machine code. And you can actually look at how this works in Python if you're ever curious. So imagine you have a function like here, I just made a little function of x that returns 2 plus x squared. There's a module called dis, which is actually the disassembler. And this will show you what Python would turn this into in bytecodes. So these are actually Python bytecodes. There's a list of Python byte operations, and here's the data passed to them. It's actually a stack-based language. This is actually what the Python interpreter sees. It doesn't see your code like this here. It looks at this. And you can see here what this function does is it loads a constant. Here, I guess, I don't know, that's an index or something like that. So it does some loading here. It's actually probably loading up the function here. It does a binary operation, so it's the squared operation. It applies a binary operation, the plus operation, and then it returns a value. So basically it's like, I think the load fast probably is the x, so it's pushing x onto a stack, pushing 2 onto a stack with this constant, probably also pushing this squared on the constant, pushing the 2 on the constant, and then it runs these things in order, and at the end you get a return value. So it's sort of interesting sometimes to look to see what your code is doing. If you're ever interested, you can use that. In general, though, what Python does is, or at least this was one of the original ideas of the person who developed Python or created it. This was Guido van Rossum, right? I think is his name. This step that turns the code into these bytecodes should not do anything at all fancy. It should just really directly translate them. Whereas if you're running C or Rust or anything else, you have this optimizer which really changes. It wouldn't look at all like this. It might optimize completely, reorder your code, do it completely differently, but to make it faster. But they wanted Python to be reliable and not do anything surprising. That's no longer quite the case. I'll show you in a moment, because actually now Python 3.13 has introduced some just-in-time compilation of this, so an optimization of this code. So there's now a sort of balance, but in general, Python does not do anything fancy for optimization. And actually, this is actually similar to other languages like Java in a way. It's done a bit different, but Java you also compile to an intermediate representation that have a virtual machine that runs what's being compiled. So the thing here, though, is to point out is that Python doesn't really do any global optimization of the code as it compiles it. And in general, it doesn't do any more what's called just-in-time compilation, meaning it doesn't look at the data while it's running and try to optimize it while the code is running. Because one of the problems with Python is it's such a language that's so dynamic that you don't tell that x is a integer even, or a float here. This could be anything. It could be an object, right? So it's very hard for a optimizer to know what it can do to this until you start running it. So the only way you could do is during you're running it, I've called my func with a float, then it might say, oh, maybe I should compile something for that. But Python right now does not do that, but it may in the future. So the point here, though, is that interpreter languages can be slow because they're really, especially Python doesn't do optimization, but also it's stepping through a bunch of instructions and turning them into machine code rather than just executing machine code directly. And that tends to be slow, right? So you're looking at interpreted statements, and that's not good. Python, like I said, is not completely interpreted, however. Even the standard library, but especially with most of the libraries that we use for scientific computing, those libraries are actually contained, fully compiled and optimized functions that were written in C or Fortran or Rust or other things, right? For instance, NumPy and SciPy. So when you call a NumPy or SciPy function, you're actually calling fully compiled code. And that's one of the reasons why you actually have to compile NumPy and SciPy before it's installed, or when you type pixie install, you're actually getting a pre-compiled version from a place, and it depends on which architecture it was compiled on, which type of computer you have, what features it has. And there's actually versions of NumPy and SciPy, I'll mention this later, though, that are compiled with special features to support modern architectures and things like that. And there's also a bunch of libraries that I'm going to show you later on, just a smattering that I'm not going to go into much detail here, but that you can use to speed up code that beyond what's in these sort of standard numerical libraries. And as we mentioned before, there's a lot of things, it depends a bit on what your code is doing, whether it's numerical or other things, what methods you should use. And I should finally say that you shouldn't always blame the fact that it's an interpreted language, that it's slow, because also algorithm design has a big impact. So even if you wrote code in C, sometimes you can have very slow code. It's just you didn't write it correctly. And so you have to think a bit always about performance. If you're worried about performance, think about it as you're writing the code. And you might want to refactor your code to improve it in the future. Refactoring meaning redesigning it in a way that speeds it up. Yeah, so that's the context here. One of the biggest things in Python that's slow, however, is loops. And that's because, of course, like I said, you have to execute a statement. When you do a loop, it's looking at each statement many, many, many times. And in scientific code, and I guess that's basically everybody, even if I don't know what you're working on, but almost everything you do, all of us here do, involves some form of looping, right? So whether it's an explicit for loop, or here's a list comprehension, these basically both execute a statement many, many, many times, and there's an overhead for each statement, therefore it's not fast. Even if you do implicit loops, I don't know if you know this, in Python you can do things like map a function onto a list there, but inside this it's just doing a for loop, and it's still the interpreter is running it. So I think this is maybe slightly faster than this, but not by much. So these things are all hidden loops. And Python loops are something like 100 to 1,000 times slower than those in precompiled languages like C, C++, Fortran, and Rust. Normally it's not a big deal because you're not looping many times, and that speed difference you don't notice, but this can become a problem, right? And I'll show you, this is something I'll demonstrate later. Yeah, and there's also other languages that are not precompiled, like I say just-in-time compiled, this way, so the word I used for JIT compiled just-in-time. So Julia and Java are examples of those. They compile mostly as you run rather than in advance, and that's another way of working. So how do you find bottlenecks in your code that are find out exactly what's slowing your code down? And that's the first topic we'll discuss here, which is called profiling. And profiling is a way to see where resources are used by a program. So that could be CPU uses, so how long it takes to compute something, but also memory resources. So it's important to remember these both. And they both can lead to slowness, but the memory especially can lead to your program crashing or just not working optimally because you run out of RAM and it has to swap to disk or something like that. This also allows you to identify very specific things like memory leaks. I'll explain what those are later on. But mainly to identify hotspots in your code that might be useful to optimize. Generally, you don't need to change everything in your code. Usually you find that actually it's one little piece that's slow, and you need to find that piece and then fix it. And I think this is very important to always ask the question, will it actually make a difference to me? So if your code is already running perfectly fine, if it takes a second or even a few minutes and you don't run it very often, stop. Don't do any optimization. You don't need to. It's working fine, right? It's only when it starts to get annoying for you that you should actually do this, because it takes effort and there's no point in doing it if you don't need it. So one of the methods for finding slowness was already shown by Max in the first lecture, or the lecture on the second day, I guess, where if you have tests implemented, you can run this, add this -- durations option. You can even put a min duration if you want for a threshold, and it'll show this case, it would show, sorry, the 3 slowest tests. And so I read it on pCoffee just this morning, and well, okay, the 3 slowest tests are test save models, load a CSV file, and save models toml, but they all take 0.01 seconds, and so I mean this was pretty useless. Like this, in this case, I would just say, okay, fine, it runs fine, there's no issue. But in principle, you might have a test that's very, very slow, and that gives you an idea where to look in your code by seeing what that test does. But this is pretty heavy, and this means that you had to have written a test that's small enough to find where in your code there's a problem. So this is not the most useful way to do it, but it's something you can try right now if you have it. And what I usually see, both in code, and by the way, is everyone familiar with Jupyter notebooks at all? So I'm going to be using them later, but it's not necessary to know how they work, but is that something people have used before? Let's say just by raise of hands, kind of a Jupyter notebook. Okay, so when I say notebook, what I mean is running Python in a notebook environment, which is basically just a fancier interpreter where you can also put text and and kind of step through different things. I'll show you in a moment that. So when you see that, I see that in a bunch of slides. But this could also just be in a piece of code that's not in a notebook also. So when I see this often though is that people do something like this. They import like the time module. They pepper their code with like start equals time. Time gets you the latest. If you call it with no arguments, it gives you the latest clock time, and then they run some code and they can make a call to it again, and then they subtract the 2 and print out how long something took. This is fine. This gives you a quick, very, very rough idea of how long some piece of code works, but it means you have to edit your code, but also only measures wall clock time. And so if you have other code running at the same time in the background, or you're doing some other project simultaneous on your computer, this will change. So this is just measuring but what you really want to know is in an independent way, independent of other things running on your machine, so CPU time is what we call that, how much time something wants. And also because, again, our computers are all multi-processing, multi-core, they're running lots of things, thousands of other processes at the same time. You probably want to have many trials and try to get a little bit of statistics, not just do it once, to get a better idea of the speed. Because sometimes you run a piece of code, and that one time it was very slow, but then the next time you ran it, it's actually much faster, and you'd miss that. Sure, yeah. Sorry. Oh, no problem, yeah. Oh yeah, to take for the notes and things. Yeah, good point. So the method that I actually recommend is actually a built-in. So this is actually a built-in module in Python called timeit, but I never actually use it in Python. I only ever use it in Jupyter because it's so much friendlier to use in Jupyter. And one thing you might know is that in Jupyter notebooks, while you're executing Python code, and by the way, this is also true not just for Jupyter notebooks, but if you use the IPython interpreter rather than the regular Python interpreter, you also get all this magic stuff, and I'll show you that too. But you get these magic functions, which are not Python functions. This is not Python. It starts with a %, but this is a magic function of the interpreter, of the Jupyter notebook interpreter or the IPython interpreter, called timeit, which allows you to automatically run a statement. You just do %timeit, type some Python statement, and it'll run that statement many, many times. It figures out automatically, it even optimizes how many times it runs it. So it can be, if it's a very fast thing, it'll run it thousands of times. If it's very slow, it might run it 2 or 3 times. And then it collects statistics and gives you back the average time it took to run it and the error bar and other things like that. And I'll show you the demo of this in just a second, but you can also do this. So if you're not using a fancy interpreter like IPython or Jupyter, you can also import the timeit module. It's a little bit harder to use, but you can, from the Python standard library, and you can actually run this in regular Python code. So it's still usable if you don't use fancy interpreters, but I find it so easy to use in like IPython or Jupyter that I almost never ever do it any other way. There's also a magic function called %time, which if you put that at the top of any cell in Jupyter, it basically just does this. But I find that's not so useful. Again, it's better to use this timeit one, and I'll show you in a second. So let's do a demo of that. So if you want to follow along here, a place to put this so it doesn't fall off. Let me find where so the demo I'm going to do is in the, let's see, where am I here? This S3 2026 lectures repo and make sure you fetch the latest version. I think, so I'm here at this commit at the main, but the last, so as of January 19th, something like that, last night. And if you want to run to, so in this here, I've added a Pixie file which installs a bunch of things that we're going to use in this lecture. And one of the things it does is install Jupyter. So if you don't have Jupyter already installed somewhere, you can just run it from here. So you can do Pixie shell in this directory and then do Jupyter lab. Can you see this? I don't know how big this is. Let's make it a little bit larger. So type Jupyter lab, and then what will happen, this will start up a Jupyter lab instance, which should look like this. It probably won't ask you for a kernel, I think, because I have it, but if it does, let me know, because that shouldn't do that. Also, since I have, but I'm gonna actually select the kernel from this notebook, which, well, maybe it will. If it doesn't ask you for a kernel, let me know, because I'm not sure, this is something I wasn't quite sure in Pixie how the kernels get organized, but we can fix that. But here, what it should look like, what you'll get, it opened my workspace here, so it would look like it's more like this. You should get something that looks like this with a blank screen. And on the left here, you see all the files in here, and we're gonna look first of all at this using timeit notebook. And so if you double click that, I will select the optimized example kernel to run it in, but I think in principle, it shouldn't ask you that. It should just run the kernel from this notebook, but I'm not entirely certain. So now, if things are working, it has no errors. So here's the notebook. And so in a notebook, by the way, you have cells that are either text, which here is a markdown, and shift return or shift enter executes a cell. So here we're going to execute this first cell, and here I'm just running, this is a Python statement here that makes a list comprehension of 10,000 elements, and it's just x squared for x in range 10,000. Is this feasible? Let me make this a little larger too. Maybe turn off the, there's a way to turn off view appearance. Actually, simple interfaces do that. That's a bit easier to look at. So I run that, and so what timeit is doing is running this code many, many times, and at the end it gives me back this answer. It says this statement takes 482 microseconds plus or minus 13 microseconds, and it ran it. Well, it ran 1,000 loops of 7 times. It ran this quite often to figure out the statistics. That you don't really have to care about. And just to show you that using here, just to show you a different way of doing exactly the same operation is making a NumPy array here with a range of 10,000 and squaring it. So that's basically equivalent to this. And if I run that in a timeit, what happens here? It's complaining. It says, oh, NP is not defined. Yeah. So let me add a import NumPy and timeit, and wait a second. And you see this took 9 microseconds, so quite a bit faster than this. And the answer, these things both do the same thing. We'll go into much more detail later on, but it's sort of, so timeit's very nice for playing around to figure out what way is actually faster to do something. So here's another example, just a really, probably a stupid one. It's not something you want to optimize, but I was just curious, is it faster to compute math.sine divided by math.cosine or use the math.tangent function? So if you were to run these, you see they give the same answer, right? So because tangent is sine over cosine of a number. But let's see which one's faster. So we put timeit this, and we put timeit that, and run it, and that takes a second. That was 77.1 nanoseconds, and this was 36.6 nanoseconds. So it was slightly faster to run it, just call a tangent function. And that kind of makes sense because if you were to look at the bytecode of this, you'd see that it would call 2 functions, and this one it calls 1 function. So it probably, you get a factor of 2 or something like that. I mean, this is something I would not worry about in most code, but it's interesting to see that things are different. Question?
If you want to run like a very small program, which maybe take a couple of seconds, I mean, maybe running it 10,000 times is not the best. So are there any option to
You don't need to. It automatically senses, because it runs it once, figures out how long it takes, and then figures out the right number of iterations. So I'll show you that in a second, that it does the optimal thing. So here it realized that it's a fast thing, so it ran it many, many times, right? But yeah, it wouldn't automatically run it 10,000 loops. I think there's an option where you can explicitly tell it what number of loops, but I've never used it because, so here's another way you can do things. So here I made just a demo. This is again, something you might do every day. I have two arrays, X and Y, that are empty lists, and then I fill those lists with a value and some function, so in this case, the sign of the value, from 0 to 2 pi. So I haven't run time it, this is commented out, the time it yet. I also implemented the same thing by doing a list comprehension. So this is the same code you might do, but written in a more compact way. Then I used a NumPy function here, so NumPy.arange, just like I did before. And then I also used a different function, NumPy linspace, which also gives the same answer. And then I did a third version where I did, what's the difference here? I actually don't remember what I did here. Oh yeah, here I used an arange, instead a NumPy arange instead of linspace, and then there you have to give it a dx instead. It's a bit more annoying. But in the end, basically these functions okay, again, I have to import stuff because I forgot to do that. Let's import matplotlib. I'll update this one thing. And so they all gave the same answer. So I plotted all these over on top of each other. They all gave you an array of x values and an array of y values, which in the function I used was just sine of x. So this is something you do quite often. You're making plots and things like this. Well, let's see which one's actually fastest here. So it's very easy to do. We can use this percent time it. So here I want to run a bunch of statements. So percent means time the entire cell instead of a single percent, which would be time one statement. And so let's just uncomment all those and run them. And let's see what happens. So this will take a second because it's going to run each one. So using the naive loops with 17 microseconds, using a list comprehension, but basically the same code, was 14.5 microseconds. But again, if you look at, within the error bars, they're not so different. Okay, a little bit, within error, they're a little bit different, but not by much. This was using NumPy. We now are a factor of 10 or something faster, 4 microseconds. Interesting, using a different way of NumPy here. I used linspace. Actually, was a bit slower. I was actually surprised by that. This is a slightly less efficient function. Although I have to say this is probably the most readable one of all of them, so I would probably stick with that. And then using this other arange method, I actually get even faster, 1.98 microseconds. So that's the fastest one. So even the way you write the code can affect the speed, even if you use something like NumPy, which is compiled already. So that means that inside the C code here in NumPy, just the implementation is slightly different, and it can be slower. Again, these are really contrived examples. These things run in microseconds. I wouldn't care about them. But if your arrays here are suddenly, 10 million elements long or something like that, then you might start to worry about it. And then you might say, okay, I'd rather write it this way than the others because it will give me a factor of 2 or a factor of 4 faster. Right? Okay, so that's why I say, also by the way, try increasing here n. So this is just 100 elements. And what I realized, this is something I found while playing with this, is that some of these NumPy functions are optimized for larger arrays. They're faster if you give it larger arrays compared to slower things. So if you make this, I don't know, maybe 1,000 or let's say 10,000, see if that's going to be too much. I run the same thing again. So now we're in milliseconds, not microseconds anymore, by the way. So again, the list comprehension is slightly faster, but not by much. It's basically the same. NumPy is significantly faster. We're back down to 70 microseconds. 77 for this different alternate way of writing it. And for the third alternate way of writing it, it's actually not much different. So once we get to larger arrays, these NumPy, doesn't matter how you write it, they start to become closer to each other. So the point is, don't over-optimize. Don't worry too much about small differences. Results are not always obvious, and often the results depend on how much data you're processing. So it's good to look sort of at a high level, which is, definitely, if you were to choose from these, you would not choose the loop one. You would try to choose one of these NumPy versions, but which NumPy version you mean? I would choose the one that's easiest to read to you, and then that's what I would use. Good. So that's how you profile something. Oh, that's a very simple way of profiling. I'll show you now a couple more advanced ways. So often, though, you're not sitting in a notebook and you're not sitting at a, or you don't have the code in a cell or something like that. So there's another type of profiler. So TimeIt is really just a very simple wrapper that, like I said, calls a function many times and collects some statistics. But what you might want to run is a real, what's called a real profile, and that's something that's actually not Python specific. Like almost all languages have a profiler built in. Python has one just called profiler as a library, but it's also called profile, and there's a second implementation called cProfile that I'll show you in a moment. And you can run it either from a Jupyter Notebook or from the command line, and I'll show you both because it's useful in different cases. But what a profiler, a real code level profiler does, you run a statement, and then every single function that's been called inside, any function inside that statement recursively. So imagine you have a statement that says, I don't know, my function of x, but inside my function, it calls 10 other functions, and those functions call other functions, those functions call other functions. The profiler will look at every single function in the entire code, everything that was ever called, and collect statistics on how often that function was called and how long you spent in that function. So this is an example here. In a notebook, you can, instead of using TimeIt, you can use prun. And what that does is runs this profiler on that statement and everything underneath it, so not just the statement itself. And you get a really detailed statistics of everything underneath it. So this is a very simple one. I'll show you a real example in a moment. But what you get is each line will be a function that's been called. It'll tell you how often that function got called. So one, or in this case, this function called, which sometimes they can look a bit ugly, but this is the create array loop function. One I had an example from a previous thing. It called it once. Inside that create array loop, it called math.cosine. It looks like that's 1 million times. So clearly it's calling cosine and sine very often, and then it did append also. And you can see the total time spent in each function, or the time spent per call, or a cumulative time, which then adds up all of these. So this is very useful to see. You can sort by the total time and see which function takes the most time. When you start to get to a real code, like I'll show you in a second, like our code, because we'll try it, there's lots of functions, and this starts to get hard to read, and there's better ways of looking at it, but the idea is the same. So, and then a second thing before I go to the demo of that is that sometimes the per function call is not what you want. You don't want to see that's too fine-grained or too, or maybe coarsely grained in some cases, that you see just how long each function take, but I want to know how much each line of code took. And there's a second way of doing that with something called the line profiler, which is something you have to install and load, but I put it into this environment. And that allows you to get a similar report, but it shows your code, and for each line, it tells you how long it spent in that line of code. So sometimes that can be nice for really debugging why something is slow, because you see, okay, it's exactly this line, not a particular function call that's causing the problems. I'm going to show you a demo of this in just a moment. But the way it basically works is in a notebook, you type lprun instead of prun, and that's line profiler run. But you have to give it a bit of extra information. You have to give it a list of functions that you want to profile, because your statement might call many functions underneath. And so if you want to show reports for some of those functions, but not all of them, if you said all of them, you'd end up with the entire code written out, and that would be a bit ugly. So you have to give it -f and then a function name. You could put another -f, another function name, -f, another function name, and then it'll give you a report on each function you decorated here, basically. So a simple case here is if you have just one function, you'd say, I want to look at the results for my func, and I want to call my func of 100, 100, and see what the profile is. So let's try that. Now I'm going to go into a much more complex example, because that I'll use for the rest of the school, because where's my Jupyter lab again? It disappeared. This is it? No. Here it is, yep. Let me make this full screen so you can see this a bit better. So I'm going to use this now. Which one is this? Profiling example is the next one I'm going to do. So this is a more realistic piece of code that I've made. So this is why I said I tried to profile a bit the code that we were writing, and I had basically found that it was super fast and fine. Although I'll come back to that in a moment. We can actually verify that in a second. That'll be the next demo. But I started to think, okay, what's something interesting I could demonstrate? And so we are all kind of in different fields, but we all do some data analysis of some kind, data science. And one of the things I know, I'm an astrophysicist. I do working with a lot of images or image-like data. And so I thought that would be a fun thing to look at. And so what I decided as a quick demo here, and you're not gonna have to implement anything here, you can just, I put all the implementations, you can just click, but just for your own interest, the example I'm showing is to take an image and smooth it by a Gaussian. So this is a Gaussian blur. So if you ever use Photoshop, that's Gaussian blur. When you click, Gaussian blur on an image, you also get it everywhere in like, Mac OS and Windows, everything is blurred, in the background when you move things around, that's a Gaussian blur. And a Gaussian blur is just taking an image, I, which is a two-dimensional array, and convolving it with a kernel K. And that convolving is just basically for loops over taking every element for every pixel in the image, you take a kernel, which is like a little mask image, you put that on top of the pixel, and you take the sum of the pixel values weighted by that mask and set the value for that pixel, then you move it to the next pixel, move it to the next pixel. I'll show this in a second, but it basically is taking some sort of mask, passing it over your image for every pixel, and using that to compute an average using the neighbor pixels around it of that particular pixel. So let's show that in a bit more example here. And that's what I'm going to use to optimize. That's a sort of real algorithm we might do. This is also useful for like smoothing data and things like that later on. It's not just for making pretty images. So here I gave you an image in this directory called casse.numpy. So I already loaded it from a astronomical file and converted it to a NumPy array, so it's easy to load. And what the actual image is, let's just plot it. Actually, I'm going to comment these out first so you can just see the image without over-plotting things, is this. So this is actually the supernova remnant Cassiopeia A, which is seen here by the Chandra X-ray telescope, which is a space telescope that's been operating for a number of years. So what you're seeing is X-ray emission in a particular waveband of a star that exploded, basically when this was 17th century, I think. And you're seeing the material, that's expanding and outwards and accelerating particles and other things in here. And so it's quite. So this image is quite impressive, but it's the sort of thing we look at all the time. And actually, I realized this image when I started playing with this example. The image here is 1024 by 1024 pixels. And actually, my examples are going to be so slow that I decided to cut out a piece of it. So what I did is just say, OK, let's take just this region, because there's something maybe interesting going on there. There's a little bit of knot in the emission. So let's just take this sub-image for the rest of the examples. If you want to try this later on, you can take, so I made two arrays here, one called image full. That's this image we just showed. And image is the one we're going to work on, which is this cutout of just this piece. So the cutout one looks like this. And that'll be much faster for the demo, because some of these implementations I made are so slow that you'd wait like 10 minutes for it to smooth an image of this resolution. So anyway, this is the image we're going to look at. It's some data that could be used. And actually, so in astrophysics, we often will take data and want to smooth it by a Gaussian for different reasons. Like we might want to, you can see this is sort of, what you're actually looking at here is the number of really photons in each pixel that hit each pixel. And so there's some noise due to just the fact that there are not many photons. And you might want to make that just smoother to get the noise away. But also what we often do is I work on an instrument that looks at gamma ray images of similar supernova remnants, but our resolution is much worse than this space telescope. And so what we want to do sometimes is take the space telescope images, blur them to be as bad as our resolution, and then we can use that to compare the two images. Because if you just looked at a high resolution image and a very low resolution image and tried to compare them, it's not so easy. So that's just some context of why I use this sort of thing, but it's used in lots of fields for many things. So the way we do this, first of all, we have to define a Gaussian kernel. This is just a function that defines a Gaussian with sigma and a number of pixels. And so this just creates a little tiny image. And this is the little tiny image I want to pass over this image on every pixel to make a Gaussian blurring. And I also defined a little function here just to compare the two images to make sure what we're doing is correct. So this just plots a before image and an after image and puts some titles on it. So you don't have to look at this, but this is just to help us later on. And then through this lecture, I'm going to go through several implementations of this, but let's first start out with the most basic implementation. Actually, I don't know why I don't think that's needed there. Or this. So this is my most basic implementation, smooth loops, I called it. And it takes the image, the kernel, and then it does basically the algorithm that I showed above, which is to loop 4 times I, J, M, N. So I, J is the height and width of the original image. For every pixel in the original image, we then loop over the pixels in the kernel, and we do some summing. There's a little bit of extra tricking here called, you see this pad in here, and that's because at the edge of the image, when you're moving this mask over the image, obviously it starts getting clipped by the edge, and so one way to do that is you add some extra pixels with blank pixels that deal with the edge effects. You can ignore that, but this is just a standard implementation of this blurring. So anyway, that's what it is. So then I run this function, my smooth loops, and I get the image, and here's the smoothed one. And so, sorry? Rotated. Oh yeah, you're right. Did I make it? Oh, I must have. Yeah, I was editing this earlier today to change the name. I think I got M and N. I must have gotten M and N switched. Maybe this is N and M. Oh no, sorry. It might be IJ, height, width, and yeah, no, that's right. No, this is correct. But I put this probably should be. No, this looks yeah somewhere. Let's see. What did I do wrong here? Yeah, it was this here. Yeah, sorry. This should be J, and this should be I. Because I originally had implemented this with some NumPy functions. I realized I wanted to remove them, so I just edited it this morning to get rid of the NumPy completely. Okay, there we go. So this is purely Python. There's no other than the images coming into it are NumPy arrays, but everything else I do, I make an output array that's really just using a Python list, and I fill that list and I turn it back into a NumPy array at the end. So this is purely Python generally. But it ran fairly quickly, right? I mean, I run this, okay, it took a second or two though, but it completed. It wasn't, but if I was doing this a lot, I would get annoyed maybe. So let's first profile this a bit. So here I can run this prun function and see what function calls are happening inside it that are slow. So this is, like I said, one way to profile it. And this shows you, so here there's not a lot of functions that are called, but the smooth loops function is the main one, right? It took 8 seconds. So actually or 5 seconds of CPU time, 8 seconds of cumulative time. So it's not super fast. Most of that you can see here was, again, the min and the max function, built-in min, built-in max. And that's because if you look at the code here, we call max here. Actually, we don't use, do we use min anywhere? No. Oh yeah, sorry, min right there, yeah, of course, yeah. So this is the clipping to a value. These get called every time for I, J, M, and N. So it's really 4 loops in here, and then inside this thing gets called for every single element of every single one of those. So it makes sense, right? So that's the inner part of the loop is the worst part. But had I not seen that that's the min and max values in there, that wouldn't necessarily tell me everything. So I might want to do a line profile instead. So here I have to load the extension line profiler first, and then I can run the same thing with the line profiler, lprun, the smooth loops function, image kernel. And this should show me per line where things are taking time. Now, this is taking a bit longer because, again, this is not a very fast function. It's running it several times. Okay, so now we have this much more detailed look. You have the entire code here, and I can see, and here you immediately see it, right? I mean, it's obvious from the code, probably reading it, but sometimes it's not obvious in real code, that as you go deeper into the loop, of course, you're calling the function more and more times. So all these inner functions get called 4.8 million times, and they take, this is line hits time per hit. So each time you call this function, it takes 373, I think this is microseconds, I guess. And we call it this many times, so we end up with, whatever this is. I can't even count the number of digits here, but it's on the order of seconds now per each one of these calls are spent in this line of code. That's just because we have loops here, right? The last function here is called once, but takes a bit of time to convert, but not a huge amount compared to these. So really, this is the stuff where we're taking time. So I think this is, again, a bit of a contrived example. It's very obvious that the inner loop is going to be the slowest part, but in more complex code, it's not always obvious, and this helps you a lot. Okay, so let's go back for a moment to the slides, because then we'll talk a bit about where to go next. So let's think about our existing code. So we have the code for pcoffee, but we don't have pcoffee running. We're not running it in a notebook right now. We haven't written anything. So how else would we have an executable like our pcoffee command line tool? How would we profile that? One thing I should mention is the module that's being run by this prun in line profiler is called cProfile in Python. It's part of the standard library. There's actually an identical module called profile that I think is still there in Python 3. This is something archaic. There's basically two implementations of the same algorithms, but the one called cProfile is vastly faster. Again, it's implemented in C. I think that's why it's called cProfile. So use that one. It's much faster. And by the way, if you're using C++ or C, there's a program called gprof, which does in a compiler option in GCC or in Clang that will do the same thing as this. So this is not really Python specific. This is very generic now. And the way you use cProfile is you run Python with the -m cProfile option, and then you give an option to where to write the statistics, so -o output stats, and then you run any script, any Python script here. For us, though, since our script is actually this pcoffee command line utility, it's a bit annoying because we don't have a script that we can run, but you can actually get around that by, rather than running the script called pcoffee, you can say -module pcoffee.cli, which is where the script is actually running, and that allows you to run Python with these options and that. And then you would run, it's good practice to put a double dash after if your script has options, put a double dash and then put the options to your script, and that basically tells Python that these options are for Python and for like pstats, and these options are for my script. You don't always need it, but it does sort of help. And I'll show you this in a second, how this works. So what will happen here is this will generate a binary output file called output, or here, actually, sorry, a typo here, I should call it prof.pstats here, and this would create a file called prof.pstats that contains statistics of exactly what we showed before, how often things were called. It's actually a little database file that then can be displayed or sorted in different ways, because sometimes if on a real program, you'll have thousands and thousands of functions that are called, so you want to be able to filter it and do things. And there's a package called pstats also built into Python that lets you work with these database files, but I'm not going to cover that because I think it's sort of hard to use, but there's really nice GUI methods to do it where you don't need to think about anything. So what I'm going to show you now is a thing called snakeviz, which will make a beautiful display of the pstats file and it's interactive. So let's try it on our code. So I'm going to go to now pcoffee. So here I'm in pcoffee analysis. Here, right? That's where I'm in your code, and I've actually checked out the day 2 solution, so I should be able to run things, right? So if I do, let's do pixie shell, so we're in the environment, so I have to type pixie every time. And if I do pcoffee-help, right? You have this pcoffee utility that Vincent created, right? So it lets you do analyze and plot, et cetera, right? So it's working. So now what we're going to do is do Python, just see that we can also run this from a script. So python-m pcoffee.cli -help. And that should be this should be equivalent to just typing pcoffee. And let's just see if that works. That I'm not wrong. Yep. So it runs your pcoffee utility. But now what I'm going to do is actually I put it before this. I don't think the order actually matters, but just to make it easier, match what I showed in the demo, I'm going to do -m cProfile. By the way, it's lower C and capital P. And then I need a -o, and I'll call it again perf.pstats. pcoffee CLI, and then let me just copy what where is my presentation now? It's one problem with having something open at the same time. I'll use the same command line here, which was analyze -d and then -output. Okay, so let's try that. So we give it the data, which is coffee productivity, and we'll give it an output file of, what is this, output.toml, right? I think that's what it outputs. Okay, so that should run our code. I think there's also an option of to show the rankings. Well, I'll leave that out for now and see what this does. So okay, this is now going to run our analysis, just as it would before. So it looks exactly like before. It worked. If you look now, I got my out.toml. See if it has something in it. It did something. It seems to have answers. So the code ran. It doesn't look like anything changed. It's exactly as if I ran it without the cProfile. But the difference is you also got this perf.pstats file, which is like 700K, and it has something in it. If you look at it, it's some binary file, so you can't look inside it. But you can install, for instance, so what I would suggest pixie global install snakeviz, because you don't need it to be installed in this environment. It's just a global tool. I already installed this. And that will install the snakeviz utility. And snakeviz will work, like I said, for any profiler, for C, for C++, for even, I think, Julia and everything else. They all, if you use their standard profiler, you can use snakeviz with it. So snakeviz just wants a file name of the profile. So that's our prof.pstats. Oops, no, what was it? What did I call it? Snakeviz prof. Why is my tab complete not working? Perf, that's why, perf.pstats. So I called it, and that's it. And if I just run that, it should pop open a browser, and it takes a second. You'll see it'll wait a moment as it's doing something. And what you see here is every function that got called in our code, including functions that are inside libraries and other things like that too. So you can see the whole code took 3.56 seconds to run. Inside that, and then it sorts these by speed. So each one, if you look at mouse over each of these on the left, you see which function was actually called. So like here, it's a bit hard to see, because maybe I can make this larger. Yeah, not great, because it's not designed for really high resolution. But like, let's say if I put my mouse over here on main, or here, let's say, so you can see on the left here, that's actually optimized.py, line 1 that's taken there, and you can see, okay, init array.py, you can see all these things being, this is actually the module being loaded, I think. And then you see find and load is being run here. So the name here is the name of the function that's represented by block. And by the way, you see the same function, you see these things like this, because this is actually, in our code, we have some loops that run the same function multiple times. And you can also see the list down here, like exactly what this cProfile thing gave before, and I can sort this as well. So when I say sort, by default, it's sorted by total time, I think. But I can say sort by, which is the one fastest per call function, that's trf.py, trf bounds. I actually don't even know what that is in here. But the number of calls, what thing do we call the most? We call, okay, these are all built-in functions, like length we call the most, but let's see if there's something interesting. That's why you have to filter this a little bit to see where, okay, so in parser.py, I think that's not in our code either. Let's see, first time there's something that's really in part of our method. Doc scrape. So this is all I think reading the data is the slowest part, basically. That's one issue, is that this code is so fast that the only speed bottleneck is reading the code. Is there anything actually vaguely slow? Not too much here. I mean, you have to get way down into the weeds here before you see something that's actually in our module. You can also sort, by the way, sort these. You can search, like if you say, I want to know how long, we have there's a function compute MSRE or something like that, right? MSE, no, compute. Oh, under metric, yeah, compute R squared, for instance. Okay, so that I filtered here, and I can see, okay, compute R squared. Okay, again, it didn't take much time in it. So we have nothing that's very slow in here right now, but that's good. So if you had a program that had a very slow piece, though, you'd see one of these boxes would be huge compared to the rest, and you would say, okay, that's the place that I want to fit. But like I said, this is the call stack here. So this is the outer function, a function that calls a function that calls a function of a function, et cetera. So this is, the deeper you go, the deeper down into modules you call. And actually, you see the thing that took the longest, actually here graphically we see, is curve fit. Curve fit, we spent 2.32 seconds in curve fit. If I click that, it zooms into curve fit, and you can see inside curve fit what it was doing. That's not in our code, that's in SciPy. But it actually took most of the time in this least squares thing, in this TRF function, whatever that does, TRF bounds. And then inside the derivatives are what took the most time, looks like, the derivative function. And if you say reset zoom, you go back to the outside here. We also spend a lot of time in this function here, fit all models, and analyze, but that's actually the reason why fit all models was slow is because of fit model and because of minpack and because of utility. So the slowest thing was this trf.py, so deep inside the fitting utility. And then the next slowest was this function called here, which was find and load, which is actually getting the data, I think, from the, yeah, and that's it. So basically nothing else. This code is fairly optimal is what that means. The only thing we could maybe think about speeding up is this, if we had a better curve fit function, a better implementation, maybe that would speed up this code. So if you had one that was twice as fast as this, our code would probably run twice as fast. But everything else is just tiny, tiny, tiny bits. So anyway, this is quite nice, right? This lets you really see how things are running, what things worked, and what didn't. Okay, any questions at this point? One thing I would say is try running this on other bits of code that you have and see what they do, and see what slows them down. It's kind of nice to look at it, and then you can just basically close this. When you're done, you just have to hit Control-C to stop that little web server that it pops up. You can also specify where it runs if you don't like that. Okay, so that was running cProfile and running snakeviz. And we showed this, in the Jupyter I showed this line profiler, but what if inside your code you wanted to also do some line profiling, and just running it from the command line just like we just did? For that, you actually have to edit the code a bit. And what you have to do, actually I think it's no longer even needed to run this, but to try it here, but you have to, in your code, import the line profiler module, in particular this profile decorator, and then you have to decorate any function you want to measure with this profiler. So it doesn't mean editing the code. You can't do it. So the nice thing about running cProfile directly is the code, nothing in your code changes. You just run it and it works. For line profiling, you have to decorate the functions you want to work, but then you get back out you can run this NumPy and you get exactly what you got in the notebook before. So I usually almost never do this. I don't ever do it in the notebook. And I just call my functions within a notebook and use the % line profiler or lprun command. It's much easier. So this is the demo we just did with the command doing everything with cProfile, right? Just make sure I didn't skip something. Yep. So just to show you, if you missed it, this is what I ran. Here I actually even used a different option. I put show rankings. So you can check if that extra function adds any slowdown. Probably doesn't. Again, this is a very fast code. And now we're going to go into the second part of this talk. And I think we're going to have a lot of time left over here because this is already going faster than I thought, to play with your own code. But how to deal with this, how to speed up code that is slow. Right? So one thing I always like to point out again is, I think I mentioned this before, this is a very good quote that's actually, even though this is a fairly modern quote, it's apocryphal and no one knows actually who said it, either Sir Tony Hoare or Donald Knuth, who are people who are very influential in computer science, said we should forget about small efficiencies. Say about 90% of the time, premature optimization is the root of all evil. So basically, optimizing your code generally, don't do it if you don't need to, because you might introduce bugs, you make the code less readable sometimes. But you should take that also with a grain of salt, because this is from 1974 in an article on why go-to statements are a good thing to have, which if you know computer science now, people say don't ever use go-to statements. So take it with a grain of salt. But I think the idea is correct, that don't optimize your code unless you have to. So the steps to actually fixing a speed problem once you've identified it is, one, always make sure your code works correctly first. So make sure you have unit tests written and that the answer you get is correct. Because as you start to optimize things, you will almost certainly break something, and you need to be able to have a reference to make sure you got it right. So don't try to optimize something before you know that the algorithm does what you want. You'll otherwise make things much more complex. Then you have to identify what are your use cases for optimization. So is it because the function's called really often, or that you're going to run this piece of analysis many, many times? That's a good use case. If, like I said, if your analysis you run once a week, maybe with some new data, if it takes 10 minutes, it doesn't matter really, because you're not running it very often. But if you're running it 100 times a day and it takes 10 minutes each time, then it's a problem, right? So again, you have to figure out, is it worth it? So again, stop if things work. But then if this is not the case, use one of these profiling techniques, and I'll show you, I'll talk about memory profiling afterwards, that's the third section, but the speed profiling here is to identify the bottlenecks in a nice scientific way by looking at the time spent in each function or by each statement, and eventually by the memory use in the same way. And then try to find just the smallest piece that's causing the problem and just fix that piece. Don't try to change everything, usually, because that'll be the simplest thing. Try to make a tiny, tiny change. And this is something we found, so in my own experience, I do data analysis of very, very large data from gamma ray telescopes, which are a bit like a particle physics experiment, where we have petabytes and petabytes of data, and we process it down to a tiny little bit of information at the end. And we always wrote that stuff in C and C++ in the past. And one of the things I introduced in the field in our local experiment was to change to using Python in it, and people were like, this is crazy, you would never do that. But actually we ended up with code that was faster than the C++ implementation. And a lot of it was because in the beginning we didn't even optimize, but we did some better code design, but then when we found the bottlenecks, we fixed two or three little tiny places in the code, and we gave us like a 2,000 times speed increase, and then the speed was not a problem anymore. And most of the code was spending all of its time in reading the data, which doesn't matter if it's C or Python, you're reading the data, and that's where the code is spent. So I'll show you how some of the techniques we use to identify those little tiny pieces and fix them in a second, but that's often the case, right? That you don't want to change everything, but you change a small piece. There are cases, of course, where your overall design is just bad, and then you have to think, and that could change speed, and that's why I put this last thing here is the overall design. If the small changes are not sufficient, sometimes you have to think about what your code is doing, and don't be afraid to refactor pieces of it. And I've seen sometimes, you realize because you built up code, over time, you started with small functions, you made it up something big. You look back and you find out, oh, on every time if I run some loop 1,000 times, and every loop I open the same data file, read it, do some processing, and close it again, then okay, refactor that, take the opening code and put it outside the loop, and that would give you a huge speed increase. So there's things like that, you can just change your design and be a bit faster. So some of the technologies that are in the sort of scientific Python universe, this is a plot from a talk that was I found online somewhere, that shows kind of some of the packages that are used by scientists and data scientists in Python. So generally, no one ever just uses pure Python. They're always using some level of higher level library built on it. And the core libraries that a lot of the numerical and scientific Python are built on is NumPy, right? So I already mentioned this earlier, that NumPy is a numerical library written in C for doing fast n-dimensional array operations, vectors, tensors, et cetera. And on top of NumPy, a lot of these things, almost everything here is built on top of that. So matplotlib, pandas, scipy, and all these things these are some domain-specific ones. scikit-learn are all built on top of NumPy. So NumPy is really the core library. It's not part of Python, but it's a core library used in numerical Python everywhere. It's actually interesting, back in about maybe 10 or 15 years ago, it didn't exist, and there was actually 2 or 3 different numerical Python libraries. They were all incompatible with each other, and the whole situation was a mess. And eventually they kind of merged and became this NumPy package, and this is now extremely standardized, and it's supported by nonprofit organizations and everything, so it's quite nice. So if you use NumPy, the first step to optimization, if you're doing any kind of numerical computations, use NumPy or something that uses NumPy underneath, like pandas, right? You already get speedups. I think in our examples here, we're using pandas, right, to load the data, is that correct? I didn't actually look in detail inside, but there's also other implementations of pandas like polars, which now are slightly more performant than pandas, and so sometimes even going to a different implementation on top of it can give you a faster result. And then I'm going to show you a second that you can, there's some libraries that allow you to compile actually Python code. So I said Python's not compiled, it's interpreted, but there's tricks you can do to take little bits of your Python code and actually compile them just in time and get a huge speed up without much effort, and that's nice. And there's other options that I won't talk about today, like Cython, which is a way to write Python in a sort of Python-like language. It's not actually Python, that automatically turns into C code, but then links with your Python code. I actually don't recommend that anymore. There used to be a way that people used it, but I think this Numba is much nicer. But you can also write code in C or C++ or Rust or some other language, and then call it from Python if you really want to have Python as your high-level interface. And I'll show you some of that as an example. But NumPy, I think, is the standard way to make things fast, right? So as I said, you want to get rid of for loops. So you want to try to think in vectors, and vectors or arrays or n-dimensional arrays. And that's where NumPy excels. NumPy, I already mentioned, is implemented in a fast compiled language underneath. I think I don't know if it still is, but there used to be even some Fortran in there, but like Fortran is a very old language, but it's very high performance for numerical computation. But most of it's C, I think, and C++. And it supports basically operations on n-dimensional arrays and with very fast transformations and slicing and other things. It can be a bit complex. But the idea is you don't call a function on many small pieces of data. Instead, you invert your problem and have lots of data and call one function on the entire piece of data at once. And that gives you almost the same speed as compiled languages. But there's a drawback, is that you have to think in arrays, and that's not always easy. So here's just basically the same example I showed before. You have, let's say you have a called NumPy function called linspace that gives you an array of 51, here in this case, 51 elements from -10 to 10. So that's a way to make so that constructs a big array. Then I have a second array called y, that's the sign of x, and here it's done for every element in these 51 elements, it's calculated the sign. Then here I also added some noise to it. I took the y array and I added random normal with a size of 51. So here it created an array of 51 noise values from a normal distribution of width 0.5 and added it to y. And then I plot it in here. So this is a very common thing you do. You make an array, do some operations on it, and plot it. So here's just an example. And here you could have done this with loops, but here there's not a single loop in here, right? I mean, the loop is hidden inside linspace, sign, normal, and the plus operator, everything is hidden for you. So in this case, I think it's quite easy. This is fairly readable. But when you start to get to more complex operations, you can very quickly, NumPy can become a burden to think about. So we'll go back to our example of the Gaussian blur, how to think about it in NumPy. It's not so simple always. So I think thinking about changing code from loops to arrays requires practice and feels really strange at first, especially if you're coming from something like C or a language where this is not done very often. So one thing that I do recommend, though, is to read the NumPy and SciPy documentation, actually the user guide, maybe more than the API documentation. And they give you lots of examples and really interesting ways to help you. I always discover new functions I didn't know existed. Like I start trying to do something really fancy and find, oh, there's just a function that does that. And so there's just thousands and thousands of functions in these. SciPy, by the way, is a library built on top of NumPy that implements scientific functions. I think do I have a slide on that? Maybe not now. And so it implements things like fitting and interpolation and any kind of signal processing, other transformations of arrays and things like that, linear algebra, et cetera. And so it's just an extension. It's actually part of the NumPy package. It's just the higher level parts of it that do algorithms that you might need for data processing, basically. So it's exactly the kind of thing we would use. So anything in SciPy that you use is automatically using NumPy on top of it. But sometimes, like I said, you don't necessarily want to rewrite your code in a vector way because the algorithm maybe is very complex, or you don't want to. It's very hard for you to think in a vector way, and you don't know the right way to do it. And you just had this sort of nice for loop code, but it's super slow. But you want to make it faster. This is something that actually was introduced actually about 10 years ago, I think, Numba. And it's kind of magic. It's a very complicated package underneath, but you almost don't have to know anything about it. What it does is it gives you a decorator called JIT that you put onto a function, and then it'll compile that function, and then that function suddenly becomes like hundreds of times faster. There's some caveats to that, but I'll show you what the caveats are. But it can even do things like create NumPy vector operations and things like this that are heavily optimized. And it works pretty well with pure Python functions, and even with most NumPy. If you use NumPy inside here, so here I don't in this particular example, but I'll show you later on that even if NumPy is inside here, it can actually optimize that. However, it only supports objects and functions that it knows. So things like if you have a pandas data frame inside this function, you call JIT, it'll just say no, I can't do it. Or there's a way you can tell it to fall back to object mode, but you won't get any speed up. So the trick with Numba is to use it sparingly, find the little function that's the slowest, just boil it down to something very, very simple that doesn't call any strange objects or other data types in there, use Numba to speed it up. And then if you call any function inside this JITted function, you also have to JIT that function as well. It's this just-in-time compiling. So you can't call, like if I have another function called, I don't know, sum internal here that I needed to call inside my sum function that I wrote, I also have to put the JIT on that function, because otherwise it won't know how to compile this without knowing how to compile the other one. So it looks like magic at first, but then as you start to use it, you realize, okay, it takes a little bit of thought, and you only want to do it on very specific parts of your code. But this is actually what we used in my own scientific code to speed up things by factors of 200 to 1,000 by just finding the one little bit of code where we were doing some, that was called very often, did some mathematical computation. We added JIT to it, and it gave us a gigantic speed increase. So it's kind of magic. The way it actually works, by the way, is also crazy in a way. It inspects the Python's syntax tree for the object translates it into a library called it uses a library called LLVM, which is what a lot of compilers are built on top of. So actually the compiler for like Julia and the compiler for C and C++ use LLVM underneath, at least in some implementations. And then it basically turns it into an intermediate representation that LLVM understands. It compiles the code, then turns it back into a Python function that looks exactly like this one. And it does it the first time you call the function, though. So it doesn't do it when you put this decorator on, it's when you run the code. That's why it's called just-in-time calculation, because it needs to know what type of array you're passing into it. So it only can compile this function when you pass in a value first. If you change the value type, it has to compile it again. So that's another pitfall, but most of the time you're always passing in the same type of value. So in a way it's magic, but again, there's lots of pitfalls, but I'll show you how that works. The nice thing is though, it has much more advanced options, which I haven't used much either, but you can even tell it to like compile it to GPU code and run it on a GPU or other type of fancy processors. So, and you can also tell it to parallelize this code if you understand parallelization. There's some dangers in that, of course, but it's quite impressive. So even, like I said, you can also apply it to code you've already written in NumPy. So imagine I have this code here, numpy.arange 1000, and then I have this function or the statement here that takes a times x squared plus bx plus c, so just a polynomial. Actually, if you were to execute this, this is not very. This looks very easy to read, and it's quite fast if these objects are quite large. But you're kind of missing some details here. That in this, when Python interpreter executes the statement, it breaks it down into substatements first, then executes each one of those. And the first thing it does is takes x squared, so it actually creates a new NumPy array, a temporary one that's not named or anything, and fills it with x squared. Then it creates another NumPy array with b times x, so that's now 2 arrays in memory. Then it does a little for loop over, then it does this operation, let's say a times x squared. So it takes this, makes a temporary array. Then it takes this expression, those two things, this and this together, it makes another temporary array with that, and then finally gives back the answer. So internally, you're actually creating a bunch of NumPy arrays. Allocating memory, by the way, takes a bit of time. So this is not necessarily the fastest thing you can do. If you write this in C, you would do it in one step. You would loop over each element, and you would do element by element the whole thing, and you'd only ever have one result array. But in NumPy, you have, in this case, 1, 2, 3, 4 of them internally, and then a fifth is the final one. So when if you were to decorate this with this Numba JIT, it would basically turn it into this code. And so you can, even with NumPy expressions, end up with much faster code by JITting it with Numba. So I already mentioned that there's packages that use these fast code, and they're already implemented fast for you. So SciPy, I already mentioned, gives you interpolation, integration, minimization, optimization, fitting, signal processing, and thousands of other things. This is written by real experts, and it comes from code even that predates Python, a lot of it. So it's really, really, like underneath, there's linear algebra libraries that were written like in the 70s and 80s and have been optimized since for every CPU architecture. So you're never going to beat the implementations of a lot of the code inside here. Not all of it, some of it's a bit slower, but generally don't try to re-implement stuff that's in SciPy. You won't be faster. The other thing I mentioned is that because SciPy is on top of NumPy, and these things can also leverage very highly optimized CPU-optimized libraries underneath, sometimes just installing a version of NumPy that's optimized for your particular CPU architecture gives you a huge speed increase. And even these things I can do internally, they can parallelize onto multiple GPUs and things, sorry, not GPUs, CPU threads without you even knowing about it. It just happens in the background, right? So you can't do much better than what these things are, so just using them is good. I also wanted to mention here scikit-learn, because I guess we'll talk about AI later on, but AI is based on machine learning, and this was a nice module for simple machine learning and model fitting. It's not covered in this lecture, but it's a nice one that I think it's good to look at, and it's basically built upon NumPy and SciPy, and it's quite nice. So let's see, we have only 10 minutes before the break, so I think it's probably best to stop now for some questions, and we can do the coffee break soon, and then come back and we'll do the demo after the coffee break. Yeah. So first question here.
Yeah. We have seen that we can test the quality of the code. So is there something to test the quality to find loops or something. They say your code is good, but maybe you can optimize it with NumPy or things like that.
Yeah, that's a good question. I don't think there's a few. So one that I hadn't thought about that, but there is sort of. Do we have a rough installed here? Right. Yeah. Right. Rough check. Checks for like syntax errors. But actually, if you look at rough check, this is something there's a help. I have to remember what the option is. That lists the. There's an option that lists what are the possible. Is it select? Well, select tells you which ones. There's a way that you can list all the different types of rules that are applied. The default rules don't include this. Let's just see. If I do rough check dash select, and I just type something wrong in there, it should give me an error message. No. Select. Can I do a dash help? Somewhere it lists, here we are, yeah. So these are all the different rule sets that Rough has. Now this is maybe not quite what I wanted. I think I have to go to their webpage, but these are all the different rule sets that Rough can run. And one of them in here is called something starts with an N, that's all I remember. Here it is, NPY, let's just do, select NPY. And then I want to do, I'm in the analysis directory, I need to go to here. Okay, we didn't find any issues in this particular code. Let's see if there's more. There's also perf. So again, then this code is pretty good, right? But there are certain rule sets that are not in rough by default if you just do rough check. But if you turn on the NumPy rules and the perf rules and a few others, it'll check for very common speed problems. But it's not going to check. It's not going to tell you how you could rewrite a for loop into a. So that's why you really need the profiler for that. But I think there's very low-hanging fruit that it will find. It'll say, okay, you should have done this other way, and it's more performant. But and I think you can give it. I have to remember what the rules are. If you look at the rough web page, I think they list all the different rule sets and what each one means, and what it'll check. But I have found a few bugs that way, or found a few places where I should have done things differently.
Maybe a related question: is there a way to integrate these performance checks into dynamic check, like you showed, into integration?
Yeah, so you can add. I think you can add. So I think by default, if you look in your .py or .py, or it's in the Pixie. No, it's probably in your .py project tool. You can add a section here called tool.rough. Maybe it's in the Pixie.
Yeah.
And there you can add a bunch of other rules. So the default rules are not very strict, and you can add a bunch of rules like NumPy.
No, but I didn't mean the rough check, not the static check, but the
profiling.
Yes, the profiling.
Yeah, I actually never thought about that, but
CI/CD.
Yeah, you could run the code in the profiler as a workflow, right? And then I don't know what you would do with that exactly. Maybe at least you would store the artifact or the output and see, or just have it print out the outs that you can expect it each time. Mm-hmm. What I usually do is there's another type of testing that we didn't cover called, which I actually don't know the best way to do, is called performance testing, and that's where you use some other service, not GitHub or some other, the two that keeps track of the speed of things over time. So every time you release a new version, it reruns a bunch of speed and it measures the speed and memory usage of each one, and then you see for each release how it changed. That I don't know which service people use now for that, but that's how it maybe be better to do it. And then you see if it suddenly jumps up, you release a version that's 10 times slower than the previous one, then you run the profiler and check. I don't think running the profiler every time maybe doesn't help you that much, and it's too much information. Yeah, okay, there's a question back here. Back to my slide.
Yes, I have a question about how you can run directly the Jupyter environment inside your IDE, like VS Code or Codium, because you show us a way to run a code externally, but how is it possible to keep the kernel inside your IDE like VS Code?
So the way, when you run Jupyter, so VS Code actually has a plugin for Jupyter Notebooks. I don't remember what the name of the plugin is. It's probably just called Jupyter, that lets you actually open and run Jupyter Notebooks inside VS Code in its own interface. There's similar plugins for Emacs and for probably other editors. I know there's only two that I know of that I've used before that will basically turn give a different UI than the Jupyter Notebook. But the other thing you can do is, and this is something I do probably more often, I do where am I here? I guess I'd exit this environment. Pixie, add IPython. It might be already there, actually. And then if you use the IPython, so IPython is just an alternate interpreter for Python. Then if you normally type, Python on its own, let me do Pixie shell again. So if I type Python, you get into this interpreter and you can do stuff. You can, print, 1 or whatever, and it does things. But then it's not really a very nice interpreter. If you do IPython, it's its own interpreter, a slightly fancier one. By the way, I have some startup code that I use for it that I don't have. That ignore these. This is just because this environment doesn't call my automatic startup code. But it gives you a much nicer Python interpreter. Again, it's the same thing. You can but this is actually the same interpreter as Jupyter. It's actually calling a Jupyter kernel here, and you can connect to this kernel from Jupyter or from IPython, and you can run this inside VS Code or any editor you want. As you just set that your interpreter is IPython instead of Python. And so here I can do time it. So time it that. Okay, I have to import NumPy as NP, and then I can run it, and then so these magic things work here. They do not work in the normal Python interpreter. The other thing I really like about using something like, this is just a very sort of side tangent, IPython, is that if you have matplotlib installed, you can do just IPython interactively and -- matplotlib equals auto. Actually, I just alias this myself always to just run. Again, forget these loader here. You can also have it automatically load modules like NumPy, which I have it like AstroPy in this case. And that looks the same, but actually now if I do something like, okay, I'll do it from, actually I also automatically, if you type pylab, it'll automatically import all the matplotlib stuff. But so here I can just do plot, np.arange 100, np.arange, let's see, sine of that. And now this is running, it'll pop up a window that's running in a separate thread, so I'm still interactive here. And I can say like, now let's do this times 2 or something like that. And the plot updates, and I can say, plt dot scale, was it? No, it's a x scale log. And now it turned it into a log plot, so I can do all the interactive. I can also, interactively type things here. I can zoom, and that's sort of nice when I'm debugging. I do this a lot where I open up both. That's not quite an editor. It doesn't quite answer your question, but you can run this interpreter and then inside your editor of choice, and you get kind of the features. It's not quite the same as seeing the entire notebook. For that, you need to install the notebook plugin, I think, for your editor, but it depends on the editor.
Just when you run the Pixie, run Jupyter Lab, you have a link to connect this with.
But that's just a web page. That link is to a web page. So Jupyter Lab runs this web page server, but it also starts up a Python kernel, and you can actually connect to that kernel. There's another URL for that kernel, that you can have. So, but you don't. If you're using the plugin for VS Code, it already starts up a kernel. It'll start up the kernel for you. You don't need to run Jupyter Lab. It's basically its own version of Jupyter Lab. They're independent. You could, in principle, connect Jupyter Lab and your code to the same kernel, but then it would get, if you edited code in one of them and not the other, it would get out of sync. So I think it's probably not a good idea. But yeah, it'll start up its own version of Jupyter essentially inside the VS Code if you install the right plugin.
So yeah, for VS Code, you should install the Jupyter extension and the Pixie extension.
Yeah, I only use Jupyter for like really, I use Jupyter a lot, but for like interactive playing with code, but I don't develop my code in Jupyter generally. Yeah.
Me again. And if when you have code, is there a way to find which part or which function of code that are using GPU?
That's using a GPU.
Because so very lot of people in my team are using GPU for all their code, and it's not necessary. So with that, I can say maybe refactor the code just to run the part of code.
That's a good point. I wonder if I've never actually tried it, but if you run the profile, the profiler again doesn't. The cProfile doesn't care, but it's not really a Python thing. It runs on the it knows what it can even look into C code. I wonder if it would be able to tell you whether it's GPU or not. I'm not sure. I think you need to probably use some special tool to know what. I guess they're using a library like CUDA or something like that, right? Yes. I guess you'd have to just look where CUDA is used. I don't know. Yeah, there's not. Do you know a way to find which bits are using CUDA code? I'm not sure.
To profile
I think on GPU it depends also on the library.
Yeah, like CUDA is different from PyTorch and other things.
Yeah, to profile on GPU, it depends on the library you use to run code on the GPU. So, for example, if you use PyTorch, you have a specific profiler for that. I don't know for other libraries. Yeah, I don't know if the cProfile can.
Yeah, probably not, because it's really designed for the CPU.
Yeah.
You probably have to have a special thing for it.
Yeah, NV profile. Yeah, okay.
But will that show you what parts of your Python code are you, I mean, that'll help you profile inside a CUDA function whether or not you get a slow part. I wonder if that tells you where
it should work like cProfile, cProfile, but for NVIDIA code. So.
I think it's always, it also shows you if there's code in the CPU.
Yeah, it's usually that's used more for the other way around to say like where should you be using the GPU, not where you shouldn't be using the GPU. So yeah, it's hard to. But yeah, I guess that's a. But I guess yeah, if you can use a GPU profiler, it should show you where that's being used at least, and then yeah.
One last question before the break.
Yep. Then let's do the coffee break, I guess, and then we come back to the demo after that.
Yeah, we start back at 11. Thanks.
Okay.